Hello, welcome back. So in the previous video, we looked at the process, a solution process called inverse dynamics, and it was a process of solving the driving forces, the effect. Sorry, the causes. If you know the motion, you know the effects. In forward dynamics, the causality is reversed. You know the forces acting on the system. You want to see what motion comes out of that combination of forces. So if I want to write it down, forward dynamics is the process. Why does it do that? The process of solving for the motion when forces on the system is known. So if I know how the forces are acting on the system, and if I know the dynamics of my system, forward dynamics is solving for the motion that comes out of that system. So in other words, goal of forward dynamics is predict motion. Very simply, predict motion, as opposed to inverse dynamics goal, which was calculate forces. So again, like last time, we can look at just a few examples how these forward and we saw inverse dynamics, how forward dynamics can be used for different contexts. So here, let's pretend I have a car and I have created a model of this dynamics of the chassis and tire dynamics and everything. So you know the forces acting on the tires because of the traction between the tires and the ground. And you know how much force is created as you turn your steering wheel. And you know all the aerodynamic forces, drag, downforce, and all of that. What you can do is simulate the motion of the car as it, for instance, enters a corner, and simulate the motion whether the car starts to slide out of the bend or roll over. So knowing the forces, knowing traction and tire forces plus our aerodynamic forces, dynamic forces, you can simulate motion, simulate or predict motion, whether you have rollover, or you can check if you slide toward the outside of the band, see what happens. So the goal here is to check, given this condition, what is going to happen. Another example, again, because I'm a human person, I'm not a monkey person. Some people study monkeys, I study humans. So this is still not used in practice, but there is lots of research on this. So imagine you have a person somebody might have some kind of disorders. So you bring the patient to the lab, you measure the movement, however they are moving. For instance, a person on the treadmill walking, and you record motion. And from the inverse dynamics that you had before, we saw before, calculate the muscle forces that cause the motion. So inverse dynamics, from a recorded motion, you measure forces. So you calculate forces and you record them. And in a predictive simulation, you can now start to run predictive scenarios. One example is a new kind of not new paradigm in stroke, for instance, when you have a muscle that is spastic, you can inject it with Botox to paralyze that muscle. Paralyzing the muscle means that it can no longer produce force. So you take all the forces that you have calculated before, remove one of the muscle forces from your simulation, and now run the simulation in a forward dynamics or a predictive manner to see what may happen after this intervention to the motion. So you predict the motion that comes out of some kind of intervention. So it was quite long. I'm not going to write it down, but predicting motion after any kind of intervention, this could be surgery or other types, is becoming very important in helping clinicians decide how or what to do with a patient. All right, so example 2, human motion. Okay, so again, let's look at the simplest case, like before, simple case when we don't have constraint. So we saw before the equations of motion equals Q minus F. And the assumption in forward dynamics is that we know forces acting on the system, and we know all effects on the system. That includes the accelerations that are caused from the dynamics of the system itself, including these Coriolis or centripetal types of accelerations that are functions of your current positions of velocities. So we know how the system is now, what are the forces acting on it. We can calculate the accelerations from this equation. So get Q double dot, and then either numerically or, if you are lucky, analytically solve for Q and Q dot in future times. So predict the motion, how the motion unfolds. Often we do it numerically. So if you know your Q and Q dot, you can calculate Q double dot. And from there, numerically, you calculate your Q dot next and integrate that over time. This is what we have been doing for most of the time in this course so far. We didn't do any inverse dynamics, if I remember correctly. Maybe a few examples, but not a lot. Mostly we were dealing with forward dynamics, predicting motion, which is a lot more fun, rather than just trying to solve something that has already happened. Yeah, okay, so this is when we have no constraints. We will see later how we can deal with system that has constraints, but just a sneak peek. If there is constraint, you still get the same kind of equation, and you can calculate your q double dots, but those q double dots, the accelerations are no longer independent. In addition to these, you also have to satisfy these constraints that are functions of your position, velocities, and maybe time. You also have to satisfy these algebraic equations. So these are algebraic. This one is a differential equation. Differential equation. That one is algebraic. So if you have constraints, what you need to end up is a combination of differential and algebraic equation. And quite aptly, it is called a differential algebraic equation, or DAE. You have to solve a set of DAEs if you have constraint. Whereas if there is no constraint, you only deal with ordinary differential equations. And ODEs, just so you know, are significantly easier and faster to solve than DAEs. So whenever possible, we like to write our equations in the minimal set of coordinates to avoid these algebraic constraints that we will have if we don't do that. So okay, that is a very rough introduction in what is forward dynamics. And that concludes this module. What we will do next are getting into a bit of how we can automate generation of these system equations, this mq double dot equals blah, 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 and how we can more systematically tackle the inverse and forward dynamics. For instance, that is what the computer software's simulation packages use. So a little under the hood of these commercially available multi-body softwares. All right, that is all we have for now, and I'll see you next time.